again.
Okay. If some of the participants audio on, I couldn't able. Okay. Well, yeah. Good morning, all. My name is Mamedi Nagaraju. I'm from Entable Technology. So, sir, somebody's voice. Sir, Arjun, sir, your
Yeah.
audio. Could you please audio off? So it will be noise coming. So my audio clear to all? I hope so. So shall we begin this session? So today, yeah, today we are going to see a lab session. So before starting our session, I would just like to ask. So we'll see the first agendas. Okay, then after we will have some questionnaires. So what are the things you have know earlier? So based on that, our session little bit uh, going to be lit changes. So according to as per our main concern is we want to be make sure that you have to be clear about the tool flow, what we are doing here and all. Okay, the present agenda we have to here design and implementation of UART. Okay, so, and what is the UART means? We're going to show some overview, not in full-fledged. So, then how it is where we use this in real-time application and designing UART. So we have our own RTL code. You can also come up with your own RTL code. It's a code is everybody have designer. They have their own code. So I'll just we have our team has designed RTL code. I will show and the simulations of test bench with the simulation. Then we'll see the functional verification of the using test bench, and then we will synthesize our design. Then we will read the reports for timing, area, power, which is the main uh, ingredients in designing your IC, UART IC. So timing, performance good, low, it should be low power and high performance. So mainly we focus here timing performance where we see the critical path. Okay, so in the critical path we will analyze the what is our critical path, how to optimize and all. So before moving to the session, I would like to ask our friends who are here, have you attended our earlier session by Nitin, our friend, our team member? uh, some any students can be unmute or you can reply to me, or sir, Arjun sir, earlier are they attended the counter program session?
Yes, sir. They have attended.
Okay. So have they practiced counter program from the RTL to GDS to flow?
Yeah, they have practiced.
Okay, okay. So they have seen from counter RTL to GDS to flow, right?
Sir, come again.
Ye- they have seen the RTL code of counter 4 bit from floor plan, also floor plan to GDS to flow. I mean physical design. Have they practiced?
Yes, sir. They have done. They have done the floor plan.
Okay, okay. Then great. So with this note, I would like to ask our friends. There is nothing different than counter 4 bit. Only difference is here our functional simulation, like our UART different design block. Okay, it's only number of your signals increases and your functionality going to be changed and RTL code little bit more. And the procedure same for as we are doing the same like a 4 bit counter, RTL to GDS to flow. So let's move to little bit more. Okay, we have seen this one. So mainly where we use this UART, it's a communication protocol. You can see here. So basically, UART means asynchronous receiver and transmitter. So if you have any peripheral device, it's going to be communicate with your microcontroller. So whatever data you are transmit here, it will receive and the receiver. So this communication protocol act as a transmitter as well as receiver. Okay, so So this is the IC mainly we use this in microcontroller and the serial data communication for transmitter section and receiver section. Then the RTL flow for this, we call it as semi-custom. Why? Because we are writing from RTL code and realizing our layout, physical layout. So we are not customizing the layout level from transistor level. So this is called semi-custom. So where we write our RTL code, this line you can see here, design with the design specifications, and we do the architecture, and everybody have their own architectures. Okay, whichever architecture is good, their report of area, power, and performance going to be good. So architecture is the key main thing. So where how to you are designing your transmitter section, what are the optimization techniques you can use. Okay, then after RTL code, either Verilog or VHDL, you can choose. Then once you run your RTL code, you're going to verify with the RTL verification tool. Here we use as from the Cadence tool called NC Lab, NC Verilog. So it's an intensive tool. So we will do using the test bench. We will give certain cases, then whether it's a functionality is working or not. If everything is fine, then we will move for the synthesis. Otherwise, we have to go back to again and do the RTL changes, and we have to check the functionality until we get the correct functionality. Then in the synthesis, it's like we do the synthesis. Synthesis is nothing but here whatever our RTL code registers transfer logic going to be converted into a logic netlist. So logical netlist, and we are going to check with the layout means timing analysis here. STM means static timing analysis. There we can find our critical path and all. If our in our synthesis, we will see a report for timing, power, and area. If all things are meet with the design specifications, we will move for the physical design. Otherwise, we will again come back to here. We will do the logic optimization techniques until we reach our timing closure. Okay. Then in the physical design, we will start with the floor planning, automatic here automatic place and route APR, and it's LEC means logic equivalence check. It's a background. It will check whether the functionality is matching or not, and the parasitic extraction, and then we will create layout, automatic layout. Then we will, after routing and layout, again we will do the static timing analysis, whether our what is our critical path here, and whether timing is in with the setup time, hold time, whether meeting or not. So this is timing closure. If it is yes, then we can go for physical verification of connections, verify DRC, design rule check, and antenna issues and all. Then we will save GDS2 for tape out. If it is not met here also, there is a iteration process here. So I would like to tell you that I want to emphasize you here in this IC design flow. From starting to ending is not one at one stretch. So we can take certain iterations. Let's say like at the RTL code level, until we get the simulation is correct, we will keep on iterate here. In the synthesis also, we will do certain constraints to reach our logic for certain performance. So like a megahertz, I want to run my design 1 gigahertz. So I want to synthesize my design with 1 nanoseconds. Likewise, okay. Unless I get the 1 gigahertz, I'll keep on synthesized until optimization. So it is optimization techniques we will use here. In the physical verification also, excuse me.
Sir, your screen is not being visible here. Sharing your screen.
Oh, I'm sorry. Okay. Hello. Um, Why nobody has said that my screen? I'm just explaining some of the slides. I thought you were all able to see my screen. I forgot. Means I already shared, but somehow it was existed. Okay. Is it clear, sir? My slides are able to see?
Yes, sir.
Yes, sir, it is visible.
Okay, okay, okay. Uh, Friends, please free feel to stop me if if I my screen is existed, or if any you want any ask me questions. Okay, it's not like a classroom tutorial. It's like a demo. So everybody be interactive. If you have any questions, you can free feel to stop me at any time. Okay. Yeah, actually, I have started from here little while ago. Our agenda is in this design and implementation of UART. An introduction, what is the UART means, and the application where we use us in UART real-time application, and the UART RTL code. I will show our RTL code. You can have also your own RTL code. That depends on RTL code is nothing but if you are good at Verilog VHL, you will get very optimized RTL code. So if you are that, it depends on newbie and experienced guys. Okay, so RTL is the place where you can learn and you can explore the coding style. And you want to become in your future as a designer, hardware means in the VLSI designer, you can work on the RTL code for good RTL. So the UART is the best design to start with your RTL code. Then after we will create one test bench for test the UART. Then verify functionality with the test bench. Either our UART is receiving, transmitting signal or not. We will check with the test bench. Then we will go for next synthesizing with the timing and area constraints. So any IC or URTS or anything, if we want to design best, we have to be as much as performance is good, means timing should be very good, and it should be low power. It's a low power, and then it should be have less area consumed. So the main ingredients of any design is performance, power, and area. We can also call it as PPA. So in our main session here, performance we focus here. Why? Because we have to be see the critical path. We need to achieve as much as high performance design. Okay, when you see in VLSI design, mainly two main designs we'll see: high performance or low power. Because nowadays area is very scaled, so you can't no need to be worry about the area. So that's why you will see either high performance designs or low power designs. So in this, our design is we target for high performance, means as much as gigahertz to be achieved. Okay. So then after we will do in the mainly focus on the synthesizing time and the netlist generation and analyzing power and reports. So this is the flow for ASIC application specific IC. You can have custom IC and semi custom. So custom IC is nothing but if you start from the transistor level, from the scratch, like a bricks kind of building house. So this is called full custom. Semi custom means if you write RTL code, then RTL code has like some kind of standard cells. Using standard cells, you will map RTL code. Then you have the bricks. So with the wall and wall, you can build your house. So this is a semi custom. So what we are going to see UART is semi custom. Okay. So this, if you feel like this is a microcontroller unit, so UART is the main communication protocol like a I2C, CAN kind of. So you can find UART. Yeah, here is the UART. It will communicate your microcontroller to other peripherals. Okay. See here, this is a application PSOC, Programmable System on Chip. In our semi-custom IC flow, we can divide in the 4 steps. In the first step, once you're ready with your RTL code, you will have the mainly before writing RTL code, you have design specification. How much speed you want to run your design. This is decided by the if you have any sponsor or any company, they will say that this is my specifications like area this much, let's say like area is 2 macro mm square, or and power should be 200 milliwatts, and speed should be 1 gigahertz. So this kind of three specifications, you can design one architecture and do the RTL code. Okay. So once your RTL code is ready, you need to be verify your functionality, and you give certain test cases in the transmitter section. Uh, so this one, so you can see here, UART means universal asynchronous receiver transmitter. So why we call it as asynchronous? Because we have, see, you can see here it is transmitting without, means clock, see, transmitting and receiving here asynchronously, and you can see here it is a peripheral here and a microcontroller, and when you transmit and receive section, it acknowledges, and the mainly it is used for serial transmitter data communication, and also you can have the parallel also, but mainly it's like a both, it can be act as a transmitter and receiver. So in the functional verification, you do the certain, give the test, transmit and use the, receive with the test case, and if it is receiving the same data, then we will satisfy with the functionality. Then if it is not satisfied, you can go back to again RTL code and do the changes until you get the uh, specified your functionality. If your functionality is working fine, then you can go for next step, synthesis. In the synthesis, you do the logic synthesis. Synthesis is nothing but you realize from RTL your register transfer logic convert into netlist. Netlist is just like a interconnected all your gates. I hope you some of the terminology you already heard when my friend has introduced the counter program and all. I'm just not going into details. So if you any doubts, you can stop me in there. So in some of the designs, synthesis also we can use DFT, design for test, along with the synthesis. But in this design, we are not going to do the DFT. Why? Because it's have some verification kind of different flow. We will do the design flow and all. So LVS means logic equivalency check here. Once your synthesis is done, whether it's changing or not, and then you will do the static timing analysis. This is the main thing we have to check our timing analysis and all, and we can find which are the paths are critical. Critical path means the path which takes more delay. Okay. So once the timing and timing, we will check it here whether setup time, hold time, some of the change means if you have any meet, we will go for again next step called physical design. Otherwise, we can go here and do the iteration process. So all these four steps are iteration process, not like a stretch from one to end. So until you get the, you every time you will do the optimization at the synthesis level for better design, and RTL code also you do for syntax checks and all until you'll get the optimized RTL code. In the physical design also you will do the better floor planning and power planning and mid the timing analysis and all. You will do the automated APR, automatic place and route, and logic equivalence check and parasitic extraction. Then again after post layout also you will do the STA analysis, static timing analysis, and everything is fine here. Timing, area, power without any timing errors and all. We can go for physical verification called verify connectivity, verify geometry, and verify DRC, design rule checks and all. So in the verify, you can also antenna issues are there, any either are designed for manufacturing or optimized performance and constraints, and we will check all these things here. If everything is done, then we will save our design as GDS to flow and we will send for tape out. So this is the flow. So we going to see, so it's a move to start. So you can see here our design is mainly in the transmitter and receiver. One is the transmitter, we can call it as one block G1 and receiver block G2. So if you have mainly in the transmitter, three transmit, hold register, and transmit shift register and control logic. So and in the receiver, receive it's like, sorry, here that receive, hold register, receive, shift register here, control logic here. So with this integrating with the bound rate generator here. So you can see here our design block diagram like this: transmitter section and receiver. Mainly in the top level we have the clock and design verification with the, we have give the input data of 8-bit here, and we will check the G1 block, G2 block in the UART block, top level. In the functional verification, let's say like our design entry, we use as verification.v file, and we will use the NC Verilog NC lab, and we will do the elaboration simulation and check the results with the waveform. So these are the, we will create first CDS lib and HDL variables, and then we will do the work directory. So this exercise functional verification will start. I hope my screen is visible, right?
Yes, sir.
Yeah, thank you. So my design, you can see here, transmitter section. So this is the top level, sorry, UART top, and I'll show you receiver, transmitter here, receiver.v file, and the test bench. Okay, so in the transmitter, you can see here, if we transmit 8 bit of data, serial data, and one start bit, one stop bit, and with a no parity bit. So when we transmit, transmit done will be complete. This is the signal output, transmit done, and it is driving by one clock cycle, rising edge of the clock cycle. So this is what inside we have say that if rising edge of the clock, when our input data is, this is a I don't want to go in details, but this is the clock here, division, and here 8-bit data. This is what data, and if it is output is active, then it will be rising edge of the, it will start your transmit, and it, once you transmit design, you can find the done. Done is going to be 1. Okay. Here we, this one, for your reference, we will consider later stage, we will share with our sir, Arjun sir, if you can also refer, but it's not like exactly like you want to be design. You can also design your own state, like this one we designed for 25 megahertz clock cycles, and also with the bound rate this one. So you can change your specifications and you can do your own UART design. Okay, and the receiver section also the same. So 8 bits receive data and one start bit, and when output, when you receive output receive, it will be high, and the these are the specifications of my design, 25 megahertz and all. Okay, once this, our top level is here. In the top level you can find UART transmitter is, we can call it as a G1 block, G2 block, receiver block, and I'm calling these 2 blocks in the top level, and then this entire design I'm keeping in the unit under test, in the test bench. Okay, so I'm just calling unit under test of my top level, and then I'm giving certain cases here. See here, I'm just applying my transmitter first, initially making 0 0 and all, clock rising 0, and then so once simulation done, we will check and the data is high or not. So this is the one small test case we have given here. So let's move to start the tool, invoking the tool. I'm going to invoking the tool. I'm just starting with the CSH C shell, then sourcing my tool installation, chRC file, location, source. So then nc launch, the tool name for simulation, and then this is the keyword for to invoke the simulation. So we use multiple steps. This is the CDS lib generation work library, and I don't want to include now libraries here, and then enter. So here first we do the, once you select this one, you will find first one is the compiler. You can see Verilog compiler. I'm just compiling first my transmitter. So there is no errors over here. If you have any errors, it will be notified. And receiver, also there is no errors in the receiver. And the top level, UART top level, no errors. I'll make sure that without errors, because I can't means in front of you edit and errors, so it would be not good. That's why I just make sure that without any errors. So you can practice when you are design. You will find a lot of errors. Then you can go to particular number and all. So in the test, I'm going to be do the test bench also simulation. So for your reference, I would like to show you one small error, so that generate one error, and we'll see if our tool is showing any error particular node. So let's say like I forgot to close here register. Okay, this is the line number. Okay, I just line number. Okay, I'll just close 1 2. Second line I close means my syntax error. I forgot to use this semicolon here, then TB test bench code. So when I'm doing the test bench here, compilation, is it test bench? Yeah, test bench over here. So now you can see here tool is showing that semicolon. You are expecting semicolon at the test bench and line number 10. So the tool is very interactive. It will be show that where you have any errors or not. So if you, so we can come down here, and we can verify our, again we can check the means we can correct our mistakes. Then we can also at instance and the go also we can edit and do the simulations and all. So once compilation okay, then we can move for next stage. Like first we need to do the elaborate. So the next step is elaboration. So I'm selecting my transmitter section, or here the elaborator here. Then receiver UART receiver elaborate, then top level, and the test bench. So once elaboration things done, the next step is simulation waveform. So I'm just directly going here test bench. Select this UART underscore TV, and this is the simulator. So once you click simulation, another window, SimVision, we call it as SimVision, it will be invoke with the test cases. So this is the simulation. If you browse, so you can see here the simulation top bench. I'm just invoking the data here. Okay, so there is no XX means it's initialized unknown values now. Okay, I'm just going to be start my simulation with the test bench. Then you can see here one case in the G1 is a transmitter and G2 is the receiver. You can see G1 values, this is the TX is transmission, and G2 value is the receiver. So in the top level, if you see here, I have transmitted the value of, so I have transmitted the value of here transmission active. So you can see here in the simulation we can see how. So receive have the results. You can you, there is a previous finish. Okay, you select the top, and so the data what we are transmitting here, you can see here the receive, it is going to be receive at end with the 0 0, and the receive section I'm going to be minimized. So the simulator, let me do the transmit also. Unable to license for simulation. Error. Once again, I got the license issue. I'll just exiting the tool. Okay. So basically, it's a advice to be take each model and do the transmitting and receiver, and then after top level, and with the test bench, then you can find the changes and all. So, okay. So this one is transmission is working fine and receiver. So at the okay at two licenses it is invoking. So are you guys following me? Hello? Hello?
Yes, sir. Yes, sir.
Okay. So we can there is a two here. What the thing is that like I have one licenses, so at the same times I'm invoking the two licenses, one for receive and transmit. That's why it is license issue. So one by one, if you open, then you can find your you have, I think, floating licenses. By mine says one license in the one user, so it is showing the license issue, no problem. So basically here the main thing is that you can be one by one, if you are compile, elaborate, and do the simulations, then you can find. So main here you can once you the top level, choose each one and select one G1 G2 like a transmitter and receiver section, and then after you can go for the like. So the area, when you give 0 0, it is transmitting and it is showing here the AB value, and the value of once the clocking rising edge of the clock, it is 1, and the serial transmission is optimize, means it is showing the received section serial. Okay. And also there is a active, when you active the waveform wise, it is going to be show the designs like at what clock cycle it is received. Okay. So once you can see here, once this design done, you can also verify here and the waveforms wise. Once you select these waveforms, okay, then so certain we can use for here default test cases of clock signals. Want you continuous simulation due to the previous finish. Okay. So it is initial values, it is taking, you can consider here initial values, we are giving the clocks per bit, and these are the time period and the clock period. you consider in this waveform, and the output values you consider at this plane. Okay, so with simulations, you can practice there you can find you have the same counter kind of program. So you have only thing is that transmission and receiver section one by one, then after you can find the test bench at the top level. Okay, so with this we can continue to be go for this synthesize. Once your design is simulation is functionalities work fine, then we can start the simulation synthesis. Well, so for synthesis, what are the input requirements? We required RTL code, right? So the RTL code, whatever we have used in the simulation, the same RTL code, I'm just going to invoke synthesis tool with the JNS tool we use it to call. So main area here we are need to be focused more points here. So how the timing analysis we use it to see and all. So before synthesis, we need certain input files. Apart from RTL code, we need constraint file. See here, so let's say like what is your constraints. So here, if you say here, my functionality is 25 megahertz working, and if you convert into the time, it's a 40 nanoseconds. Okay, when you do the simulation time, you have 25 megahertz and so you can also, this is not like a, you can do the changes like a 25 megahertz is little bit less, so we can optimize, keep on. Okay, so we want to go for higher performance means it will increases. So that's what, if you are 50 megahertz is good, if you are 100 megahertz or 1 gigahertz, it is going to be good design. So the create clock is the input file, and this is the time, and waveform you can see 0 to 20. So this is a rising and falling. If you have 40 clock, it's a rising is 0 to 20 is rising and falling. So one rise and one fall. And then input is I clock. This is my input clock in my top level. And the rising is 0.4. This is the default like a input. You can see clock transition time. This is as a constraint we use it to, I'm giving here 0.4. So this one depends on your 1% of your like 1 to 10% of your period. So this is also equal 0.4, and certainty 0.05. Uncertainty is nothing but, so some clock, all the registers you have certain uncertainty get the clock, so you have the 0.05. So this is called the TCL script. So this set clock transition is the mandatory TCL script. I think our Nitin has introduced you what is the TCL script, and all the same things I'm using here, the timing constraints. Okay, and apart from this transition uncertainty, you have input transition time 0.8 nanoseconds, and here another input delay and output delays, giving here 4 nanoseconds from clock to all inputs and outputs. If you not give these clocks, the question is we can't get the timing reports. So timing, we need to give the certain timing input and output, then we can reach our clock input to output, then only we can find our critical time, critical path. Okay, so and another one is set load is default, it's for all outputs, and the maximum fan out we can have the 40/20 here, also you can reduce also. So this is default, these two things are default, you can depends on the design. Okay, specifications and all. Now my constraint file is ready, and then tool is once Genus tool, so you can GUI show. So the design you can see here, there is no design, empty. In the now we are going to, so another apart from SDC, we need one TCL script for this synthesis. So synthesis in the step where we write our library files. So library files we have to be show the path. We are using here 90 nanometer and the location of the library path. So the 90 nanometer location, you in your work directory also you can find in the installation directory. Foundry, digital, 45 is there, 90 nanometer is there, 180. So I'm accessing 90 nanometer. So this is the path. So in this path, we use for library lib file for synthesis. You can have fast lib, slow lib. So these two things we access. The library you find is a timing information of your standard cells. Okay. And lib files have the layout informations of 90 nanometer layout exchange. When you are doing physical design, we access the lib file. So this path I have given here, library path, and the RTL path. RTL path in the next RTL folder you will find dot means current working directory and RTL folder. So I'm just using the fast lib. You can also use the slow lib for better performance purpose. And RTL codes, I'm taking the RTL top.v file, transmitter v and receiver v. Okay. So here, then we are again doing the elaboration of our design top. So in this command, it will elaborate our design, and the design check for unresolved any timing issues. This will generate our test means timing reports, and then after it apply for SDC file, synthesis design constraint SDC. So this is what we discussed SDC file. This it will apply all these constraints at this stage and read SDC at constraints for top.sdc file. So this is the .sdc file. Then synthesis effort level, I'm keeping this one is medium stage, synthesis generic mapping and optimization effort level. Okay. And the generic mapping and synthesis, this is the ultimate command. It will be optimize your synthesis. Done. So once done, you can write your output files. This is the write file. Write HDL 90 nanometer netlist file, it generate with the UART netlist, and write SDC file generate with the SDC file. Then PPA reports, performance power area reports. You can find here report. I'm going to be save as in outputs 90 nanometer folder with the UART power RPT report. RPT means report, and then a report for area, same UART area report, and report for timing, area for timing report. Okay. And also number of gates, gate count report, and the finally quality of the results, QOR, and that is going to be also be here. Okay. So then after you can use show. So this is not required because it will be already we have our okay, you can keep it. So that will be your synthesized netlist come with the GUI show, graphical user interface show. Okay. So apart from my RTL code, I have SDC file ready and TCL command is ready. So TCL commands, you can keep it one by one, like for actually one by one, you have to copy here. And once you open the tool, so you have to apply one by one here. But it's a time consuming process. To avoid this one by one at a time, all the commands we will give with the TCL script, tool command language script once at the go here. Then your command line genius tool will take and invoke all the commands and the one go from one here to here. Okay. So I'm going to be exit GUI here, hide GUI, then source my genus underscore script TCL. So source genus underscore script one dot TCL. So now you can see here in my work directory. In this work directory, there is no reports ready here. Once ready, once our design is synthesized, then our reports getting ready. Well, once the entire design is executed, you can go for this log file. It is created this all data in the log file, and also it will be come up with your synthesized netlist. So here you select this your design schematic main window. So you can see this is our synthesized netlist. GUI existed. Okay, 1 second. Abnormal exist. Okay, maybe the tool is issue. Okay, I'll just once again run this tool. So earlier, what when we are synthesis our design, now you can see find all the reports here. The log file is here, and once synthesized reports you can see here. First one we report, we will see the area report. How many number of cells? Now you can see with the time signature and the UART top. So the total cells in the transmitter section G1 108 cells, and the receiver section 103, total 211 cells count, cell count, and the cell area, net area, and total area. So you can see here total area here. This is the area report. Then after number of gates based on how much dynamic and leakage power. So basically, this will help when you write any research paper to be published, how much leakage power you are at the synthesis stage, and the total power you can find in the nanowatts. And then our main concern here, timing. So timing, this is the timing report. So in the timing report, you should be clearly see, we ask 40 nanoseconds. Okay, you can see here 40,000 picoseconds it is showing, and it is reached, means 40 nanosecond means 40,000 picoseconds. Okay, but one path it is reached here 35,480 picoseconds, means it is came little early than what we expected. Okay, so this is called slack. If let's say like I have asked the 40,000, and it is reached by this value, and you have the saved 35,480, the slack means. So before the slack to be introduced, I just would like to show the timing related slide. These slides I'll share if you are want. I will share with your sir. Then you can refer later. So in this synthesize, we are HDL with the Verilla code synthesis tool representation, and this is how it is synthesis map, and the out RTL code and gate level netlist and reports ready. So this is the library path, and this is the library inside your technology library file. It is look like cell functionality and all. This is the SDC file. I have explained what is the SDC file and all, and the timing related information. And this is the common synthesis design constraints. So these are the constraints we have given here. The same constraints I kept here in this slide. So this is the synthesis captured netlist. This is the power report, timing report. Okay, here slack is, you should know the importance of what is the slack name itself. Slack is defined as difference between actual and achieved time. So let's say like arrival time and required time. So required time is 40,000 and arrival it's like a 5,000. So what it is means 40,000 minus 5,000. So 35,000 your slack. So slack, if you have the positive slack, arrival time before the required time. If you are negative slack, arrival time after the required time. So I would just like to know if your positive slack is good, then your design is definitely will work. If your negative slack, then means it will be your negative slack means your some of the registers not trigger at the right time. So how do I one real time I will would like to explain what with the some example. Let's say like you have been want to take the lecture, so you have informed all the students their hometown means they are sitting their home, so you have given the time schedule for the lecture. So all the students, they have come their own way with their mean of reaching the lecture hall. Some they reach before, they have the positive slack, means they have reached in time. Okay, means before the session, that is called positive slack. If they are after the lecture start, if they came some of the students later, they have the negative slack. So that means, let's say like your lecture time is the register, if it is a before, it is coming called setup slack, and if it is after certain clock rising edge of the clock, it should be positive, means the data should be arrived that time, so that is called a positive slack. If it is not means not ready at the time at the rising edge of the clock, you are going to be negative slack, that means one slack. So so if it is a positive slack or zero slack, we call it as a timing is perfectly meet our designs. If a negative slack means timing violations. So what type of timing violations? You can find the hold violations and setup violations. If this slide is understood, sir? If any students, can you say, is it okay now here? Because until unless you understand the slack, you can't analyze the timing report and the critical path. Are you getting? Are you? Hello,
Yes,
the
sir.
student. You clear with this Slack information and all?
Yes, sir, it's clear.
Okay. Yes. Thank you. So with this Slack, we will analyze our report. So now our design. Okay. Here I'll just the tool is existed abnormal, so I'll just restarting my genus script file with the new time signature. Then our design, you can see once then actually earlier we used to get here, but we need to be select our top level, and then in main, so this is the main and this is the receiver. So we have selected some of the log files are creating problems, so I'll just need to be clean the log files. So just give me a second. So once your synthesis is done, you can see here what are the terms and what are the nets here, netlist, and the modules here, receiver module, and also receiver model separate. You can schematic view. So in the schematic, then after you have the receiver model G2. You can also see your schematic view, and then you can also then after you can see here timing debug. So we write we have to analyze our timing path. So this is the timing paths. So this is the bar chart. You can call the long timing paths and the short timing path. So there is total paths are 96, and the passing paths, all paths are passing. There is no errors here, no failing paths. And WNS means worst negative slack. This is called timing violation. Means it's a negative slack, and the total TNS is the negative total negative slack. Okay. So whenever you have this one is timing violations, and I'm selecting, these are my paths. So I'm selecting which are path is more taking. Say, see here, this path taking 39 picoseconds. So I'm selecting this path as a color with the red, and select highlight in the path. So if you select this path, so the path where it is traveling from source to, this is the source G1. In the G1 module, our main from register 1 to, from clock to Q in the D flip flop, and the delay and the sum. Okay. So the load, how much it load it taking. So then after it is going for NOR gate of 2 input from B to Y, and then after clock inverter, AOSL, NAND gate, D flip flop. So it is coming from D flip flop to 1, 2, 3, 4, 5, 6. So 6 cells are there from here to here. It takes in, taking from the delays, each delay, how the taking and all. So this is a positive slack, so there is no timing, but it is taking 39 picoseconds. So it is arriving with the very early. So here we have so much positive slack. Positive slack so much means we no need to be if you even very use slack, positive slack doesn't give you a good performance. So we can optimize positive slack a little bit more, means we can tightly constrain. Let's say like you, instead of 40 nanoseconds, you can ask the tool to come 20 nanoseconds. Means if your delay is decreases, your performance increases, right? If your f equal to frequency equal to f equal to 1 by t, right? See, 1 by t means frequency equal to 1 by delay. If your delay is decreases, means inversely proportional, your frequency increases. So this, in this constraints, it is your slack is more. So I'll just avoiding this one, and trying to constraint, very optimizing my timing constraints. So what I have to do, I have to change my script here, especially my constraint here. So I'm just giving here 10 nanoseconds. 10 nanoseconds means you can find here 100 megahertz. So you are going to be executing at 100 megahertz, and the 10 nanoseconds here for report. And then I'll make this one rising and falling is 5 nanoseconds. Okay. So you can keep it, this is default. You can also, okay, this is 1%, you can keep rising and falling. Uncertainty you can keep, and transmission, and this one is 1. Okay. So this one save, and the script here you can give here power report netlist file for, okay, keep it netlist file for 10 nanoseconds. Earlier was 40 nanoseconds, right? So I'll just making new reports, 10 nanosecond SDC file underscore 10 nanosecond SDC file, and the power also 10 nanoseconds, area also. This is the reports for different than 40 nanoseconds. So because if you are not change here, it will overwrite your 40 nanosecond reports. Okay. Now save my design. I am just constraining little constraining my timing for more optimization. Like instead of 40 nanoseconds, I'm just giving 10 nanoseconds, and we'll see the reports. Then I'm directly going for synthesis debugging timing report. Now see here in the timing report. So here total 90 paths and there is no failing paths. Till it is earlier you can see the bar changes. So some of the paths are now increased with the timing delay. So now you can see here the total timing delays. We can get the report from report timing. Now I asked to come the 10 nanoseconds, 10,000 picoseconds. Now it is tool is reached 8,485 picoseconds. Still you have the positive slack. Okay, slack of 8,485. So still you can be optimized. Can you see here? So now the path are going to be changed. Earlier it was G1. Now the path is going to be changed for rising and falling, and the gates are changed NAND gate, D flip flop. Now with the again we can also optimize here. Still it is a positive slack. I'll just going to for new constraints. So now you can change us two things you can be observed here in our reports. There we have in the physical design reports. So outputs, their quality of results. You can keep these two things here. Quality of results of 40 nanosecond, 40 nanosecond here, and the quality of results here 10 nanosecond. Can you see? So in the 40 nanoseconds, the paths are like total cell area 1525 cell area. Now 10 nanoseconds your cell area, there is no changes here much. Okay, the power leakage total power 29,000. In the 49 you can see the total power is 1,14,482 nanowatts, but in 10 nanosecond you can see here 2,93,000, means power is increased. So what do you mean? If you are optimizing for power performance, power is degrading from quality of results to here QOR quality of results. Okay, now the fan out here and the timing paths, it is saving here 8,484 is the critical path slack. You can see here critical path slack, but in the 40 it is see critical path slack is 35,482. So another constraints also we will give with the over constraints. So let's say like a 40 is the you know, unreliable constraints, 10,000 is the reliable constraints, and I'm just giving one more constraint called over constraint. In the over constraint, I'll giving here 0.2, 200 picoseconds, and the reports like it here not even in 1 nano, and so it's more than like a, it's like a 2 gigahertz. You can say I want to run instead of megahertz, I want to run my design 2 gigahertz. So nowadays all the processors are running with the gigahertz, right? 2.5 gigahertz, 3 gigahertz. So I want to run UART with the 2 gigahertz. So 200 picoseconds, and 0.1 is the rising and falling. All things are, I'm changing this one. So this is a VC constraint. Now I'm just coming out from the timing report of 10 nanosecond. So here actually what we are doing here, we are trying to give the constraints for optimization. Okay, so I'm just giving here my new constraint file called VC over constraint. Then so also reports also we need to change, instead of this one, this for 0.2 nanoseconds, and this too also 0.2 nanoseconds. Basically you need to maintain one Excel sheet where each nanosecond what is the power, frequency and area reports. Okay, so so now some of the windows I'm closing some for clearly to see. Yeah, some terminals I opened the tool, that's why it is showing the issues of tools. Okay, I'll just close for clearly. Now good to go. Then I'll exit the earlier tool. Now I'm opening for our constraint design. So there is a three cases. First case 40 nanoseconds, one case, and second case is 10 nanoseconds, and another case is 0.2 nanoseconds. So three types of constraints. One is a reliable constraint, over constraints, under constraints. Okay. So I'm now applying over constraint case. There you can find timing violations. So some worst negative slacks. Now I'll just GUI, I'll keep it aside, then see the report timing. Okay. Now you can see here, now paths are, one path is violated 174 picoseconds. I asked to reach 200 picoseconds, but it is taking 174 negative slack. So negative slack means what are the timing paths has changed. So now we can see in the GUI report timing debug. So now you can see the red color is, earlier we have the green color. That means the similar means your synthesis netlist will work with the green color. But when you see here red color means these all violated paths. So this is the long, you can see here this is the long path. This is the path, it is taking more delay. So now you can see here 124 minimum and the required. So you can, we'll check it. This is the path taking and we can visualize the path when we physical do the design. So now we can see, click on this, what is the path traveling. So it is where it is traveling. So it is data, path setup and negative slack, violation, uncertainty. So this is the color code you can see, and the path how it is traveling from clock to D flip flop, or how it is traveling also you can see here with this. So path 96. Now you can see total paths are 97 and the passing paths are 24 only, and failing paths are 73. So this is not work. So this is called over constraint. When you are over constraint, your design is not, you can't your design doesn't work real time. So that's why we are avoiding this over constraint. Now we will see, analyze three reports together. One is under quality of results of 2. nanoseconds also we will open. 0.2. Yes. Are you guys with me? Hello, sir. Is it is it okay? I'm I'm giving I'm giving continuously. Are you getting or not? Means I just would like to pause station this and want to ask your. So here I just would like to summarize our synthesis. Here 40 nanoseconds. See here, this is a 40 nanosecond report, 10 nanoseconds report, and zero point 0.2 nanosecond. This is the under constraint of 40 nanoseconds. This is the reliable constraint of 10 nanoseconds. This is the power constraint. Okay, in the power constraints 0.74, and also you can see here power is 8 lakh 16,000. Sir, somebody's mic on. Could you please? Okay, thank
Yeah,
you.
1 second. I'll check.
Now I okay, fine, sir. Fine, sir. Now you can see here under over constraint, you can see 8 lakh nanosecond nanowatts power, but reliable constraints it is getting only 2 lakh power, and 1 lakh nanowatt for the under constraint. So among all these three, which one we will go for physical design? Netlist file. So every case you have different netlist files. 10 nanosecond netlist file is the reliable netlist file. So in the 10 nanosecond report, we can take the synthesis. From synthesis to physical design, we will take the 10 nanosecond netlist, this one netlist, and this one. So these two are output files of our synthesis netlist. So we will take these two files, netlist file of our synthesis output files, netlist file and SDC file to physical design here. Okay. Now we will start the physical design. Are you guys okay? Now you understand that the synthesis I'm giving uh, discussion 5 minutes for discussion. Are you guys understood? Synthesis stage. Excuse me, sir. 2 minutes.
Okay, sir.
Yeah, I'm back, sir. I had just water. Thank you so much. Uh, at this stage, are you understood, sir? Synthesis and all. What is the means under constraint, over constraint, and reliable constraint? Three things are important things. Hello.
Yes, sir. It is clear now.
Okay. I hope all the you can also try with the different cases each and every time you can optimize the design. And it's not case synthesis is a stage where you can have so many iterations. So that's why I just would like to take so much time here. And remaining place and route is a little bit automated, so it will be very quickly we can do. But at the synthesis stage, analysis is takes more time. Okay. Now, with this note, I'm going ahead for the physical design. The physical design input file is SDC file and the netlist file. So this is the SDC file of 10 nanoseconds and netlist file of 10 nanoseconds. And then before physical design, we need to prepare like a TCL file for the design view. In the design view, default view, where you can find our uh, SDC file location. So this one is 10 nanosecond SDC. I'm just editing here. The location of our timing library is same like a slow lib and fast lib. So same like synthesis, we are showing the path of our libraries, and then RC corners, okay, and then minimum and maximum timing here, okay, SDC delay corners here. Okay, this is the like a default view for technology files to show. Okay, and then the same thing also globals. In the globals also you can find our netlist file location. This is our netlist file location. So I'm just giving 10 nanoseconds netlist file location of my design. And the left file layout, this is for physical design verification. Net left file location I'm giving. Okay, remaining things are default. So these two files are like your counter program also might have these two files. So only you need to edit here left file location and RTL verilog netlist file location. These two things only you need to changes the default globals. Remaining things are same. So once done your two things, this 1 to 4 is ready, then you can click. See it, I'm just opening my physical design tool. The tool name called Invoice. So once design, you can see not in memory, there is no designs in the memory. So now this all entire physical design is like auto GUI based. I'm just importing the design. So I'm just loading here first the global files, the global file, default global file. Once you given, you will, it will find all your where your RTL code, whatever I added in the global file locations, it comes layout left file location, VDD and VSS input, power nets, and I have given VDD, and nets VSS I have given. And then configuration of SDC file location, so you can timing analysis purpose, and the location of your constraints file. So this is the constraint file. Everything is, it took the default. So mainly you can find here constraint file. So this is our constraint file location, SDC UART SDC underscore 10 nanoseconds. Okay. Now once this timing analysis purpose, we keep it that SDC file. Without SDC file, we can't analyze our timing here. And then once design is ready for import, then click on import design. So you can see 0 errors. warnings are ignore. Warnings are just say that it's suggestions. Okay. After design import, you can find the design is imported here. So if you click uh, zoom zoom out, can keep zoom out. So this is the flow receiver. This is the transmitter. Okay. Two things are there, subblocks. So now you are ready for the floor plan. The first step is floor plan, specify floor plan, and you can keep it aspect ratio. Aspect ratio means height and width is 1. That means height and width is 1 means square. And the core utilization, I want to go for 70% of my core utilization. Okay. And you can give this one core to IO boundary 10 micron, sorry, 10 micron all. Unit wise 10 micron, you can see downtime and the height and all default I kept. Okay. Then now you can see here your floor plan is ready. Then next one is power plan. In power plan, you need to connect some global pins. The global pins what we are using here, VDD for power and apply for all and VDD power. So add to list. Then also ground, VSS ground, VDD and power, then apply. Now, then once you applied, now next stage power, add the rings. So these steps, each and every step importance, my friend Nitin has explained. So I'm just quickly moving forward. I'm taking the bottom and top as a metal 9 and right and left taking the metal 8 and giving the default of 1.8 space. Okay. And it is look like this one. I'm for this side, left and right, I'm metal 9, top and bottom is metal 9. And this is the power ring I am creating. Okay, this is inside you have the core boundary and your standard cell sitting that place. So once done, okay. So now we can see here VDD. So this is the VDD VSS, VDD VSS. This is the main power supply to your standard cell sitting in this place inside your core area. Next, after you need to go for power plan, add stripes. The stripes for VDD and VSS. Okay. And metal 9 you can go for, and you can keep it horizontal, same width and all. So number of sets you can go for 5. Okay. And the remaining things are default. So this one in the next one, stripes means you will get the stripes like this, vertical stripes, horizontal stripes. Okay, to give the power and all power reports. So now you can see here power stripes are came in between and across your core area. Okay, now stripes ready. Now you place your standard cells. So no, before placing the standard cells, we need to connect these power connections, and all. That is called special route. You go here, route the special route, VDD and VSS, you select, okay, and keep it all, then run. Now you can see here VDD and VSS connected to your main supply, core ring VDD and VSS. So this is routing with the bias, with the main source. Then once ready, good to go for placements. Place standards as run the placement, and so here mode you can keep it IO pins here, place the IO pins and all. So remaining things you would default and run. So in the placement step, you can find all your standard cells are placing. Okay. So there is after placement completed, two errors are, it is related to the scan chain. There is no scan chain in my design. You can ignore this error. Remaining warnings are suggestions. Okay. Once placement done, you can find your design like this. Your design is placed here. Okay. Once placed design, you can also see the, I'm disabling metal layers here. This is the design placed. Okay. Earlier you have, this one is, earlier you have this the pins here, and these connections are here. This is a receiver and transmitter. So once your design placed, this is the cells you have transmitted. This is the transmitted, and this is the receiver, and this is the received cells. So once cells are placed, so what we need to do then, after we have to go clock tree. So we need to do the clock tree. So clock tree purpose, it's not like GUI based. So we need to write again here scripting. So I want to emphasize here, in ASIC design, especially synthesis and physical design, more works like a scripting languages. Like that's what, if you want to start your career in your life as a physical designer or synthesis, you need to know the scripting languages like a TCL or Perl language. So here we are using TCL command language. In the TCL command language, we are also using physical design for these commands. So this all defaults like a metal 1, 2, 3 related information, and then this command will create the clock tree first. It will see what are the clock to be required, and the buffer cells it will be insert, inverter and block. So what it is means, it will give the all clock connections to all your standard cells with the buffers and inverter help. Okay, and it will be route your clock net, and this is the run optimization. So you can see here cadence clock optimization, CC optimized design. With this command, it will be optimize your clock, and it will be report your clock skew reports. And skew is nothing but, if any of the register, let's say like in your standard cells, means I think genus is open still. Okay, I'll just close. Okay, in the inverse, let's say like in your if this cell is getting long, this is the clock from here to here, it is getting little than this cell, that is called skew. So skew nothing but, it should be have less, means all the standard cell get the at the same time of your clock. You can see here, this is the clock pin. Actually it is a clock pin connection to all the cells. So that connections we need to give this one. This is the clock pin. Once you, this link, once you route, means metal layer, you will see the link of this pin. Okay. Now at this stage, I'm just showing this clock, and then save the design as CTS encounter. So with this name, it is saved with the stage called CTS stage. Okay. Now remember, once tomorrow, means when you want to open your design at the CTS after complete, you give this file, it will be invoked where you have stopped your design. Okay. Let's say like once design is ready, I'm just keeping all metal layers on. Okay. Now I'm minimizing, I'm just giving from my command, design command here. So this is the design command for, okay. Now here, source of CTS dot tickle command. So my clock is routed. You can see here, once the clock route, okay, clock debug. So your clock pin to your cells. So this is the sync pin, and this is the source pin. This is a source pin, and this is the sync pin. And all the clocks which are related, skew reports, and these things are reported here. Okay. Once this, also this is the clock. You can see here clock connections, and I just want to show the clock how it is netted. So I'm just disabling signal net here, special nets here, power nets here, ground net here. So this is the clock net. Can you see here clock? So the clock is going each and every cells, okay. And if you are ground net, this, okay. Now clock is done, clock synthesis done, then we can move to route. In the route section, the routing, I'm routing to all our cells. The fixed antenna and insert diode, these all things I'm just giving, and then route. The final stage, you will find all the nets are going to be route, either signal, power net, clock net, all things. So now you can see here nets are routed. If you are nets wise signals, okay. Now you can see here routing. And earlier we have seen the clock. So which are, this is the net is going, and this is the receiver, and this may be clock. Oh, no, not this one. So if you select this, so each and every signal you can see the nets are routed. So once okay, clock is disabled, that's why it is not showing. Now you can see this is the main clock, you can see high clock, and metal 2, this is the called metal 2, this metal layer. With the metal 2, it is routed your entire design, and each metal have its own color, okay. That's why we have different colors, metal layers. Then after, finally you can go for report timing. Oh, okay. Post report, you can see. So before timing, we will verify our design. So verify geometry. The verify geometry, you have all the minimum width, maximum width, these all conditions. Okay. So width total is, these are conditions for verification, minimum and all. And once you're done in your report, so this is for synthesis. In the terminal, you can see here verify geometry. It is started from verify geometry here, and there is 0 violations and 0 warnings. Verification is completed. Okay, verify geometry without 0 violations and all. And then next, verify connectivity. Any connections are missing or any connections are unconnected, hanging, open, short. These all things are checking with this verify connectivity. Then verify connectivity report also you will get it. So there is no issues with the verify connectivity. All things are no violation path. All things are corrected. Then verify DRC, design rule checks. So in design rule checks, each technology have design rule checks. It also we can see the, if verify connectivity and verify geometry is okay, then DRC almost it completes. So now there is no violations in the DRC, design rule check. DRC are fine. The final point is that we need to see the like a clock path. Okay, so I'll just show the clock path, which one we require. Debug. So to see our critical path. So debug timing, debug, and select. Okay. Report. So report, we can see the report and all after placement. So this is the time paths here. So let's say like this is the path, it taking more. Okay, we select this path. Now it is take required time more. So let's select this is the path 134 nanosecond. I'm giving this one color as a green. Oh sorry, which one we give other than this? Okay, shall we go for light pink? Okay. No, this is not visible. We'll go for yellow. Okay, yellow itself, and highlight on this path yellow. Okay, so this is the path. You can see here critical path. It is starting from here to here, here to here. So there are so many logic levels. And also some another path also we will see. This is one path, and slack more, whichever slack more we will see that. So this is a slack is, so we can go for this path also. We can give this one is a red color, and highlight on this path red color. Okay, now you can see here, this is one path is coming from here. It is going loop and like this roaming with the, there is a breakages. That means some logic standard cells are there through this one. So it is not showing standard cells. So you can be like a cells if you are cell shape, in cell blockages, cell layout. So there is a it is like only the signal traveling places it will showing. Okay, it is disabling your report is displaying your standard cells placing and all. Okay, likewise you can choose which one is the bar taking more clock cycles. That is the called critical path. And the failing paths are there, passing paths. So you can be change the optimize the design. Still you get the better slack. Post negative slack is very 420 nanoseconds are picoseconds are there. You can optimize. So here it takes the iteration process to be rectify your failing paths. 13 paths are there. These 13 paths. So to avoid these 13 paths, sir, I think I'm just going little bit optimize. So this is one you can do optimize design and do the optimization. So you can decrease the paths for optimization of setup. Okay. Okay. So it is like a, you can optimize your design. So you can post CTS, select, okay, then doing the optimization. So if your some paths are failed, now it is optimized. You can see here some paths, violating paths are 13, and setup time is passing all the paths. Some violating paths are still 13. Now you can, it is trying to optimize. You can go for here ECO, engineering change order, where you can optimize your design automatically. Then you can go pre-CTS stage, and the pre-CTS stage with the incremental and go. So the tool is optimizing. You can see optimizing. Once optimizes, it will try to correct. So until you get its iteration, so there is paths are passing all the paths. Okay, there is no max and priming DRC violations related. There is no worst violations. Everything is cleared. So there is some stage you can find hold violations that you can optimize. So we finished at the route stage. This is the routing, and also we have debugged our design for timing while critical path. Then after the final step, you can save, verify. We also verified design geometry and all. The final, you can save your design, save design GDS2 file. So my GDS2 file is called UART dot GDS. So this is the GDS2 file we say give to the fabrication unit people. So then they will give the IC. So I'm just saving the design. The output of our design files, and the thing is the final file name called GDS file. So this is the file. So this is the encrypted file. We will share to the fabrication unit. Okay. So this is the output file. Now let's say like the final thing I just would like to say, I just have saved the design one stage. I want to invoke the tool. So you can save my design as invoice top dot enc. Okay. Enc is the encounter top dot enc. I'm saving my design here in this stage after routing, and I just closed today, and tomorrow I want to see the design at where I have stopped. Okay. Now I'm just opening the tool once again, and I'm invoking the tool where I stopped earlier stage. So restore design, invoice, select your file. This is the file UART top inc, and January 14th at this time signature. So open. So the design is invoke the design where you have stopped. So now your terminal will see finished successfully, and the design is opened where you have saved your design at the routing stage. Okay. Sir, with this note, I would like to end my session. Sir, I'm over to you, sir. Any doubts? We can have the discussion here.
Yeah. Thank you for your session.
Thank you, sir.
So I'll definitely get back to you if some doubts arises.
Mhm.
And,
Any participants, sir? Participants?
participants are in the lab. Like, only I'm the one. Few students were absent.
If they have any doubts, they can ask.
Okay. Students,
Sir,
any
could you
doubts?
please share the recording session?
Sorry.
Sir, they are asking for the recording sessions.
Could you please share this recording session?
Yeah, definitely. I will share the recording. So I've recorded the video.
Why my session is it very boring, or all the people are left because I keep on continuing the steps? End of the session, only 4 5 students are there.
No, these are the absentees, sir. Some students were absent to the college. Most of the students are in lab, like they are displayed it on a projector.
Okay, sir. That is good, sir. Actually, you have recorded the session. Otherwise, again, repeating the same sessions is going to be very tough, no?
Yeah, right. Procedure is very lengthy, so I thought of recording it and sharing it to the students.
Yeah, sir. Sir, here I just would concentrate mainly synthesis and flow physical design.
Mm-hmm.
So in the verification in the simulation, there is some issues in some of the data to be transmit received in the license. I really not explored the simulations. Mainly, I want to be show synthesis and physical design. Yeah.
Okay.
I
Yeah.
hope you got the means, flow what
Right.
RTL to PDS2
Correct.
flow.
So you got the flow, like how to proceed, and all the new terms like Slack, all the things they have been explained very well. I'm
Thank you,
sure
sir.
that students will be able to execute the programs now.
Sure, sir. Sure. Thank you.
Yeah. With this, let us wind it up.
Yeah,
I'll
sure.
Thank you once again.
Thank you for your valuable participation.
Thank you all. Thank you.
Yeah.
Good day. Bye.
Bye.
Thank you, Arjun sir.